Hello everyone, today we will look at a nice geometric interpretation of something that more or less we've all learned in trigonometry class, which is to express a sine theta plus b cos theta in the form of a single trigonometric ratio, including this length r and this angle alpha. So much of the inspiration of the video, this video at least, has come from Grant Sanderson from the channel 3 Blue 1 Brown. He always inspires his viewers to make all sorts of connections between different areas of mathematics. So this is how we've learned it in algebra class. So take a sine theta plus b cos theta. Let's equate that to r sine theta plus alpha. Now let's expand r sine theta plus alpha. Now from the formula for sine a plus b, we can expand this as sine theta cosine of alpha plus cosine of theta sine of alpha. R sine theta cos alpha plus r cos theta sine alpha. So now we can see that the r sine theta plus alpha looks kind of like this expression right here. So if we call this equation 1 and this one is equation 2, we can write so equating the coefficients of sine theta, we can write r cos alpha is equal to a, and r sine of alpha is equal to b. We can name these equations 3 and 4. So basically the use of this entire expression right here is to find the minimum and maximum values of a sine theta plus b cos theta. And the way we find this out is, well, I'm just going to be very brief here. I'm not going to delve too deep into the algebra over here. So from here we can get r is equal to, the positive root of a squared plus b squared, and alpha is the arctangent of b over a. So from there we can solve for r and alpha, and then we can find the minimum and maximum values. So let's take an example over here. If we take 5 sine theta plus 12 cos theta. Now from this expression, r is square root of 5 squared plus 12 squared, which is 13, and alpha is the inverse tan of 12 over 5, which is 67.4, we'll say. So this can be written as 13 sine theta plus 67.4 degrees. But now we will look at this entire expression in a way that, in a completely new way. Excuse me. And I'm going to have to put the camera down for a few times because I can't hold the cam. I need to draw with both hands, and well, I don't have 3 hands, so anyway. So what do we have over here? So A sine theta plus B cos theta. A sine theta and B cos theta. Well, one way we can look at it is if we take a right angle triangle with hypotenuse A and this angle theta, and then we take a similar right triangle over here let this hypotenuse be B and this angle be theta. So A sine theta could mean the opposite side of this triangle, because if we think of this as let's say x, so sine theta is equal to x by A, because opposite over hypotenuse, so x will be A sine theta. Alright, so similarly for this side right over here, since cosine of theta, we can consider this adjacent side to be B cos theta. Again, using the same reasoning, so cosine of theta is opposite over adjacent, which is y over b, so y is b cos theta. And so what I'm going to do next is keep this triangle in place and rotate this triangle so that A sine theta, this side over here, is on the same straight line as B cosine theta. So what I've done over here is I've taken this triangle over here and rotated it so it lies on the same straight line. So now maybe we can see some patterns over here. Like if you play around with this long enough, you'll start wondering. So if this is theta, then this should be 90 degrees minus theta. And now, so since all of these lie on a straight line, let's call this angle C. Therefore 90 minus theta plus C plus theta equals 180 degrees. So if thetas on both sides cancel out, and C turns out to be 90 degrees. So over here we can see that we formed a right triangle over here. So now we have two of these existing right triangles over here, and we also have a third right triangle with sides A and B. And now I'm going to draw a straight line joining these two. So yeah, now once I've joined these two sides, we can now call them we can call this new hypotenuse r, and this angle right over here alpha. So now we're very close to what we're looking for. And we can see the significance here. R corresponds to the hypotenuse of a triangle of sides A and B. So which is why we got the R is equal to square root of A square plus B square right over here, and the alpha is the angle tan of alpha. The tangent of alpha is B by A, which is what we found right over here. And so how do we get r cos theta plus alpha from over here? Here's how. If you rotate this and add an extra line over here, and extend a perpendicular, excuse me. So now I've drawn a perpendicular line from this over here to this, and since all of these are right angles, we can say that this is a rectangle. But anyway, that's not the point. So over here we can see that the angle theta and alpha, the sum of these two angles is an obtuse angle. And how do we find the sine of an obtuse angle? From our unit circle definition, the sine of an obtuse angle is equal to the sine of its complement. The sine of its supplement. So the supplement over here is 180 minus this. So back to our figure over here, we can see that the sine of theta plus alpha right over here is equivalent to a sine theta plus b cos theta. And now how do we do this? So let's consider this side as D. Sine theta plus alpha is opposite over hypotenuse, D by R. And so D happens to be R sine theta plus alpha. And so we now have our proof of our geometric interpretation of a sine theta plus b cos theta, which also happens to be r sine theta plus alpha. And we can say the same thing about a cos theta minus b sine theta, in which case it will equal the cosine of r times cos the cosine of theta plus alpha. So now we have labeled this side a cos theta and this side b sine of theta, and by now hopefully you can get the reasoning how. So over here we know from our trigonometry class that a cos theta minus b sine of theta can be written as r cos r cos theta plus alpha. The r cos theta plus alpha. So b sine of theta minus a cos theta can be written as minus r cos theta plus alpha. And by similar reasoning, you can say that this side equals to r cos theta plus alpha, but over here it's minus r cos theta plus alpha. So, well, we can show negative values geometrically, but the fact that it's virtual, the fact that it wasn't originally there and we had to extend it, could probably mean that, like, account for that negative sign. But we can only say that the absolute value of a cos theta, so r cos theta plus alpha we can say that this is b sine theta minus a cos theta, since subtracting this from this gives you this. Anyway, so what we can write is that the absolute value of a cos theta minus b sine theta can be written as the absolute value of r cos theta plus alpha. So this is the piece of I don't know, geometry that I wanted to show you guys today. And now may your daily math be less daunting and more meaningful to you.